Welcome to the Adaptive Computing booth again. We're going to have Marek Magryś with Cyfronet presenting now. I'll turn the time over to Marek.
Okay, so hello, my name is Marek. I'm from Cyfronet. A few words about what we are and what we do. So Cyfronet is the first Polish supercomputing center, established over 35 years ago. Currently we are hosted by AGH University of Science and Technology in Krakow, Poland. We provide free computing resources for scientific institutions all over Poland, mostly from our region, of course. We are a center of competence in cluster computing and application optimization, so we do all the stuff to help our users do their calculations as efficient as possible. We've been the proven partner in most of the big European grid computing projects. I will mention a few in a moment. And currently we host Zeus, the most powerful supercomputing device in Poland. So in terms of projects, we've been taking part in many of them. The biggest one, national, currently is Grid Plus. Wow. And we're also taking part in big European projects like EGI, WLCG or PRACE, which you might be familiar with. In terms of Zeus, its current configuration is 350 teraflop. We are ranked 106th on yesterday's top 500 list, which gives us the first place in Poland. What's interesting about Zeus is its construction, as it's not an uniform hardware-based cluster, it's heterogeneous. So we have a number of CPU nodes, number of fat nodes with which are 4-socket node and large memory. We also have a number of GPU nodes and VSMP nodes. In fact, this VSMP machine used to be the largest one in the world just last year. Now we've got there's just a bigger installation somewhere. So in terms of what we really use Zeus for, it's mostly chemistry. I know it's mostly chemistry. We also do some physics and some grid computing. And in terms of grid computing, I can find is LHC. In LHC, Cyfronet is currently the largest tier 2 in the grid. We do about 1.5% of all LHC computing, and that gives us 1.5% of chances that this is us who found the Higgs boson. In terms of Moab and how do we really do job scheduling, it's quite an interesting story, because Zeus used to be rather a small cluster with just hundreds of computing cores, with mostly serial high throughput with one core only. We used to use Torque with all the versions you can see on the slide. We were doing our scheduling with Maui. We used to have only 2 submission hosts, which didn't really make much traffic to the system. We didn't have any local user of this machine at this time. Face. Okay. Wipe. Okay. Now it should be better. So we didn't have any local users, so the number of problems we needed to face was a bit smaller. But then we decided to build all our institution HPC around Zeus. So Zeus was extended. We got some HPC workloads, we got many local users, now it's about 1,000 of them. new kind of jobs appeared, like many core jobs, many node jobs, large memory. Some GPU cards were also bought, so we needed to do something with these GPUs and scheduling jobs across them. And Maui couldn't do this for us. We had some ideas how to fix it, but it would take too much effort. The cluster usage was at most 60% because of all of these scheduling problems. Despite we were doing really many things to improve this. And new gateways, which have been installed, started to generate more and more additional load, which finally just Maui couldn't handle. So the workload which really appeared started to be really heterogeneous. We had regular CPU jobs, we had GPU jobs, we had serial jobs, threaded jobs, MPI jobs, and finally SNP jobs. The memory range of every job was very different. It was from hundreds to terabytes of memory, and wall time from minutes to even months. Even we don't really like such. So in terms of how the workload is really composed, local batch users, so these who just use our user interface, log in there and run their jobs via batch system directly. It's only 26% of all the number of jobs, but they consume 60% of the computing resources. So this is a significant part of our workload, which is the most important currently. We are now in Zeus, we have 1.4 thousand nodes, which is of course managed by one batch server. We have 7 different submit hosts, 7 submit gateways, which gives us significant traffic to the scheduling system. Last year, when Zeus was not at its full power yet, we had over 7.5 million jobs and 60 million CPU hours, which gives us rather high job throughput, about 22,000 jobs daily. As you can see on the graph, on the blue graph, the number of jobs is really different. It depends on the week, it depends on the users, and with all this and Maui, which wasn't able to really manage, we decided to try Moab. We knew Maui very well. We used Torque already, so Moab was kind of a natural choice. We gave it a try. We asked Adaptive for evaluation for 45 days. We did migration from Maui to Moab with our configuration, in fact, in less than 1 hour. So only for 1 hour, new jobs were not being launched. Just few simple configuration file changes were needed. We've managed to migrate the scheduler and preserve all the running jobs, so nothing really bad happened to the workload running on the system then. And the evaluation in general went very good. We were happy with the results. Scheduler commands responsiveness improved, which is kind of important for the administrators, you know, to just run the command and not wait tens of seconds to the result. We got much faster scheduling cycle completion. As far as I remember, with Maui, we were not able to go below 5 minutes in the end, and with Moab, it's about 15 seconds now, so very, very short scheduling cycle. No more scheduling deadlocks, no dead cycles. In general, utilization of the machine rised, so now we get around 90% in average. The highest utilization I saw was 97%, so it's really very good, but because of the different job types, it's not really possible to get to 100% because some resources are always waiting for new jobs to be launched, even though we use backfill, of course. So our batch system contains from one resource management server with Torque and Moab. We have 7 gateways, so one local user interface. We have Unicor gateway, one QCG gateway, two G-Lite gateways, and one Globus, via which users can submit their jobs from whatever place they like. We also do extensive monitoring of the infrastructure, so we use Ganglia, we use Zabbix, we use our homebrew software. In fact, we needed to implement some local cache to the data to be able to do some analysis, more or less real time, of the workload being run. And currently we have, as I said before, 1400 nodes. The number of cores is wrong, it's 20,000 cores now and about 200 GPUs. We still use Moab 6.1 and Torque 2.5. The Torque thing is just related with stability. It's proven to be working fine. We also don't have any problems with Moab with this version, but we are thinking about migration. I will say a few words later on. So what we are really doing with Moab, which we were not doing with Maui, is, for example, better memory management. In general, killer, so out of memory killer, is a very bad thing if it happens on your computing node. And we found out that Red Hat 5 or Scientific Linux 5 tends to kill processes which are not really the best ones to kill. So, for example, in our environment, PBS-mom was very often being killed. We've done some optimizations of out-of-memory killer score, which is possible, so you can score the processes, but still it wasn't really enough. And low memory, despite all these problems with killing system processes and killing jobs, of course, also occurs with problems with file systems, which generally can bring the whole node down and unusable. So we've done all the historical data of our jobs that we had. We established a default memory limits for each queue, because we have more or less the queue shows the type of the workload. We have over 20 queues now. We prevent jobs from running on nodes which don't have enough memory or very little memory left, and 95% of memory issues were just gone. Now we are working on better memory usage monitoring to make task killing more accurate, because as I said before, you can adjust, you can point killer to kill the right job, but you need to be very careful, and you need to tell him what should he do. And to tell him this, you need to know what was the job requirement, memory requirement, and what's the actual usage. So in terms of disk management, we also had a number of jobs which tend to consume a lot of local disk space, because despite, even though we have a large shared storage file system, we also have a number of nodes which have their local drives, so we can point some jobs to the local drive. And this has this disadvantage that you can really easily fill such a hard drive up, which causes many very interesting problems, even maybe not even job problems, but also some system ones. So we have established minimal local disk space requirements for various job types, for various queues. As with the memory, Moab prevents jobs from running on nodes which just don't meet the disk requirement, and we got rid of the no space of left device errors almost completely. So with some other stuff we're doing with Moab, it's like there are things like fair shares. So we do resource sharing for the users by fair shares. Some big groups can have access to a static reservation of resources, but in general, everything what is static is rather bad, because you waste some group of resources. So fair shares, in our case, were very good. So we import SLAs from a system called Bazaar, which is used in our NGI initiative. So each user which has an active computing grant can be sure that statistically he will get the time that he really needs. We also have some advanced resource reservation mechanism. So we defined some partitions on which 2 of 4 middleware that we support can create their own reservations for jobs. It's sometimes useful, and we have users which already use this feature. We also have dedicated resource pool for whole node jobs, which allowed us to shorten the time of the time of the job of the queue of the job. This is a static reservation of some resources, but the queue can go even further below this, so this is very, very good for the users. We also have some non-MPI partition dedicated to serial jobs, one-core jobs, just to keep them at one place. We also do automatic blacklisting of black hole nodes, so we got some of the nodes which were failing like hundreds of jobs because of some problem that our health check scripts were not able to discover. So now we just blacklist them by default. If number of job fails in a very short time, we can see what's really going on with there. In terms of the future, we're planning to move to Moab 7 and Torque 4 with C groups, and this is related to migration to the new version of Scientific Linux. So we are going to move from Scientific Linux 5 to Scientific Linux 6, probably early next year, and we plan to launch Torque 4 with the new Moab then. We also plan to do some proactive job efficiency monitoring. So if a job efficiency defined as CPU time to wall time ratio is low, we can notify the user, and if it's very low, we can just kill the job automatically. So that's something which would also improve the efficiency of the system. We also plan to integrate Zabbix monitoring with Moab REST interface, because you can get some interesting information from Moab directly via the API. This is very convenient. We also plan to use some of our Ganglia metrics to improve the scheduling process. For example, we monitor the average I/O load on the local hard drive, so we can omit such nodes with scheduling new jobs. We also plan to do some green computing, so turn off unused nodes. There are not really many of them, but still you can find some. We also are thinking about just lowering the frequency of the CPUs and other stuff like this. As I said before, we need to improve our job memory usage monitoring and implement job removal if PBS mom is unresponsive or the node just went down for some hardware reason, just to user know that the job is dead and he needs to run it again. Okay, and I think that's more or less it from me. If there are any questions, I'm glad to answer. This is view of our computing room, and that's it.